Alright, so we're going to do, once again, I've got my little son Sammy helping me out with this. We are going to do two more examples of using augmented matrices to solve linear systems. But again, we have two weird cases when there are infinitely many solutions or no solutions. So let's see some examples of this. Let's first try to solve the following system. And the following system looks like negative 4x plus 6y is excuse me, well, that's just stuck in there. I'm not going to edit that out. Okay, negative 4x plus 6y is equal to 8, and 10x minus 15y it's not a y, 15y is equal to 3. So first we set up the augmented matrix, which is negative 4, 6, 10, negative 15. That is the coefficient part of the matrix. What's that, Sammy? Oh, I want to put an 8 up here and a 3 down there. Exactly. Thank you, Sam. 4 months old and already doing linear algebra. Good job, buddy. Okay, so again, the first thing we want to do is to get a 1 in the upper left-hand corner. So what we're going to do is divide by negative 1/4. And so we're replacing the first row by negative 1/4 the first row. Negative 4 divided by negative 4 is 1. 6 divided by negative 1/4, well, I'll let you do the arithmetic, but that's going to be negative 3 halves. And 8 divided by negative 4 leaves us with negative 2. And down here I've got 10, minus 15, and 3. Now the second thing we want to do is to get a 0 down here below the 1 that we just put up here. And the way we're going to do that is, well, if I multiply the top row by negative 10 and add it to the bottom row, negative 10 plus 10 will give me 0. So I take negative 10 times the first row plus the second row and replace the second row by that. Negative 10 times the first row is equal to negative 10. Negative 3 halves times 10 is equal to 15. Negative 10 times negative 2 is equal to 20. And again, our second row is equal to, what's that, Sammy? 10, negative 15, and 3. You see something funny there, don't you? You think that's kind of funny. You've got negative 10 and 10 here, and 15 and negative 15 here. What happens when I add them together? Well, when I add them together, negative 10 plus 10 gives me 0, 15 minus 15 gives me 0, and 20 plus 3 gives me 23. Well, so we get the row equivalent matrix 1, negative 3 halves, 0, 0, and the constants are negative 2 and 23. Well, that's a little weird. There's no way that I'm going to be able to get a 1 over here because I've got a 0 over here. Keeping a 0 here, there's no way I'm going to get a 1 over here. So we're actually kind of stuck. Let's stop and see what linear system this corresponds to. The top corresponds to x minus 3 halves, so this corresponds to x minus 3 halves y is equal to negative 2. Fine, that's just some equation. The bottom corresponds to 0x plus 0y, so that's 0 is equal to 23. That is not true. Yeah, Sam, that's right. It's not true. It's silly. So this is actually inconsistent. You don't like that, do you? There are no solutions. He's having fun right now, don't worry. He's sitting on a little jumper, bouncing around. You dropped some of your toys, though, buddy. Yeah, you did. Oh well. So there are no solutions. So actually, in general, whenever we have a row which has a bunch of zeros in the coefficient part, and then a non-zero thing in the right part, there are no solutions. So whenever we get equivalent to something that looks like, say, 1 m n 0 0 k, something like that, this is going to be inconsistent and will have no solutions. So whenever we get something that looks like, let me highlight this, this, we have no solution. 0, 0, k, and here I'm assuming that k is not equal to 0. Okay. Great. Or maybe not great, depending on how you feel about that sort of thing. So let's get rid of this, and let me get rid of that highlighted row. And let's do one more example. And let's take the following and try to solve. Let's take 3x minus 6y is equal to 12, and negative x plus 2y is equal to negative 4. So this corresponds to the augmented matrix 3x minus, just 3, I get rid of my variables, minus 6, negative 1 because the coefficient on x here is negative 1, and 2. And over here I get 12 and negative 4. Now I want to get a 1 up here, and really I could do it many ways. I could switch the two rows, so I would have a negative 1 up here, and then I could multiply the top by negative 1 to get rid of, to turn this into a 1. You don't like that way. You're saying that's too many steps, huh, Sammy? Why don't we instead just divide the top by 3, because that'll turn this into a 1. I think that's what you meant by that, yeah? Okay, so we'll take 1/3 the top row and replace it by the top. Replace the top row by that. 3 divided by 3 is 1. Negative 6 divided by 3 is negative 2. And 12 divided by 3 is 4. On the bottom, I still have negative 1, 2, and negative 4. Huh. Well, now I want to put a 0 down here, and it looks like if I just add the first row and the second row, I'll get a 0 right here. So let's take the first row plus the second row and replace the second row by that. That's perfectly valid. It doesn't even need to be a constant multiple. It could just be the first row. So what I get is, and Sammy's excited about this, is 1, negative 2, 4 on top, but 1 plus negative 1 is 0, negative 2 plus 2 is 0, and 4 plus negative 4 is 0. What linear equation does this correspond to? That's weird because I've got all zeros in the bottom. The top is x minus 2y is equal to 4, and the bottom just says that 0 is equal to 0. Well, this is true always, so in fact, we're just looking at the solutions to this equation, which are the points on a line. So the solutions are the points on the line x minus 2y is equal to 4. Now we're going to write this out using, again, a parameter. And to figure out how to do this, first I'm going to solve x minus 2y equal to 4 for one of the variables. And I'm going to choose the variable that it is easier to solve for, and it looks like it's easier to solve for x. So let's do it for x. X minus 2y is equal to 4. So x minus 2y is equal to 4, and to get Sammy, I'm trying to talk right here. I'll add 2y to both sides, and I get x is equal to 2y plus 4. Okay, these streaks are getting from happy to unhappy. So let me finish this in a second. Alright, Sam said I could finish now. So let's go ahead and do this. So I solved for one of the variables, say x here because it was easier to solve for, and I'm going to let y, let's let t be a parameter, which means that t can be any number. Then we let y be equal to t, because y is on the right side here, so I'm going to describe x in terms of t. So y can be any real number, and x, since x is 2y plus 4, it will be 2t plus 4. So my solution, or my solutions rather, are given by, I can write it as x is equal to 2t plus 4, and y is equal to t, where t is a parameter. T is going to be any number. Or I could write it as an ordered pair, 2t plus 4, comma t. Okay, so that just gives us a description of every single solution to this equation. Okay, so let's summarize what we just saw. We were using row operation. Well, we started with a system which looked like AX plus BY is equal to H, and CX plus DY is equal to K. And from this we got an augmented matrix which looked like A, B, C, D on the left and H, K on the right. And then we use our row operations to bring ourselves to one of the following scenarios. If I can get down to something like this, let's just write M and N here, then this tells me that there's a unique solution and that this solution is x is equal to m and y is equal to n. If I end up with something that looks instead like, say, 1, let's put like S here, M, 0, 0, N, this bottom row here, and let's say that n is not equal to 0, this bottom row right here tells me that, and let me highlight that, let me do that in green for kicks. This bottom row right here will tell me that, along with the fact that n is not 0, tells me that there are no solutions. And the third possibility is to have something like 1, S, M on top and all zeros on the bottom. And what this will tell me is, because I have nothing but zeros on the bottom, this will tell me that I have infinitely many solutions. And I have to write them out using some sort of parameterization, which we discussed before. Alright, that's it.